This is lecture 1 for module 8 in the book Problem Solving Guide for Mechanics and Thermodynamics. The subject is rotational kinematics. Rotational kinematics has many useful analogies to the description of motion we did in the first couple modules. So instead of distance x, speed v, acceleration a, we have angle theta, angular speed omega, and angular acceleration alpha. So instead of distance, you want to know how many rotations it did, how many radians it rotated around. If something's rotating, the average angular speed is the angle divided by the time, just like average speed. The analogy to acceleration is the change in the angular speed divided by time, delta omega over delta t. So for example, RPM per second, radians per second squared, something like that. So the best way to see how it works is to actually solve a problem. So here's the cyclist starting from rest, increases the angular speed of the pedals from 0 to 150 rotations per minute over a time of 10 seconds. What is the angular acceleration of the pedals? I don't want to use an equation for this. I want to think about it. Starts from rest, it's a standing start, gets up to 150 rotations per minute over 10 seconds. How quickly is the speed, rotational speed of the pedals changing? And you should be able to just write it down by now. It's 15 rotations per minute every second. After 1 second, 15, after 2 seconds, 30, 3 seconds, 45. When you get up to 10 seconds, 150 rotations per minute, which is 2.5 rotations per second, which is pretty good, especially if you're in a high gear. So part B, how many rotations do the pedals make over the 10 seconds? By the way, here's some different units for that. Alpha, that angular acceleration, 1/4 of a rotation per second each second, 90 degrees per second each second, 1.57 radians per second every second. So the average rotation starts at 0, gets up to 150. The average angular speed is 75 rotations per minute. 75 rotations per minute is 1.25 rotations every second, and you do that for 10 seconds. 1.25 rotations every second for 10 seconds. The angles through which the pedals travel through in this time is 12.5 rotations. All right, 12.5 rotations. That's theta. Should make sense. Let's get the angle with some different equations because I want to introduce these rotational analogies. So we have this equation for linear motion. X is 1f at squared plus vit. In rotational motion, it looks very similar. We just use the Greek letters. Theta, the angle through which it rotated, is 1/2 the angular acceleration t squared plus omega initial t. So we can plug in numbers for this. The angular acceleration is 1/4 rotation per second squared. The time is 10 seconds. We're going to square that. The initial angular speed is 0. So 1/2 of 0.25 is 0.125. 10 squared is 100. The answer is 12.5 rotations, which is what we got with the average angular speed. How about this equation? V final squared equals v initial squared plus 2ax. What does that look like? Well, we have omega final squared equals omega initial squared plus 2 alpha theta, angular acceleration times angle. So we have the final 2.5 rotations per second, which is 150 rotations per minute. Started at rest, the angular acceleration 0.25 rotations per second squared. Now we can solve this for theta. 2.5 squared is 6.25. 2 times 0.25 is 0.5, so 2 times 0.625 is 12.5 rotations. Same answer we got before, not surprising. There's really not much sense in me going over a bunch of problems like this. You should be very familiar with one-dimensional motion. The only difference is we're doing angles instead of distance. So you have to solve the problems yourself to develop the skill. There is one thing I'd like to talk about, relating translational speed to linear speed. If we have the very special condition of a wheel rolling without slipping, then, and only then, we can relate its linear speed to its rotational speed. You can imagine if a car is rolling along, the wheels are rolling, the faster the car's going, the faster the wheels are turning. There's a direct connection there. All right, so here's a wheel rolling along without slipping at constant speed. The general expression for the distance it travels is r theta. R is the radius of the wheel, theta is the angle through which it goes. And we can check this by figuring out how far the wheel travels when it goes around once. So one revolution is 2 pi radians. And multiply that by r, we get 2 pi r. This is just the circumference of the wheel. So if it goes around once, it's going to go one circumference along the ground. Should make sense. To get to the speed of the wheel, we just divide both sides by the time. X over t is the speed. Theta over t is omega. So v is omega r. Not true in general, only rolling without slipping. And I emphasize this because students apply this when they shouldn't. Only true when the wheel's rolling without slipping. If you have a pool ball, somebody hits the pool ball with topspin, right? It's not going to be rolling without slipping. Somebody hits it with backspin, it's not going to be rolling without slipping. You throw a bowling ball down the alley. Generally, it's not going to start out rolling without slipping. Eventually, if you don't throw it really fast or with a lot of spin, it's going to catch up. It's going to roll without slipping. As with linear motion, these equations are only good if alpha is constant. The angular acceleration has to be constant, or else those are no good. It's best not to remember when the equations apply. It is best to understand when they apply, because the exams are going to test your understanding, not your memory. That's lecture 1.